कुछ गड़बड़ है.
Yes, sir. Now started.
Now starting. Okay,
Yes, sir.
that's fine. पता नहीं वो तो बुलेट मार्क था. ठीक है. Now I'm going to start. Okay, let's see. इसीलिए मैं पहले स्टार्ट करता हूँ because I am not very comfortable with these things, computers and that. If something goes wrong, then it becomes difficult for me to recognize that what is the problem. Okay, so that let me recall that what I was doing that. So X was a non-empty set and Px, actually it's a linear space, vector space of all real valued. Later on I made a comment, if complex valued also similar thing you can do it. It doesn't make a difference. Vector space of all real valued bounded functions on X. The function A, so that means you have all these real valued function from X to R and bounded. Bounded means range is bounded. Is a bounded subset of R. Since I am taking bounded, so I can define this metric for a pair of elements in Bx. Fg belongs to Px, where you define sup fx minus gx over all small x. Since fg bounded, so f minus g is also bounded. Remember, f minus g actually is f plus minus g. So look, this is a vector space. So since g is bounded, minus g is bounded. F is bounded. Sum of two bounded functions is bounded. So this is a metric. Is a metric on Px. Okay. Last time I said, given a metric space, your first concern should be whether Bxt is a complete metric space. So here my claim is that Bxt is a complete metric space. When you have a complete metric space, we correspondingly we say that means we say that D is a complete metric. D is a complete metric means this is a complete metric space. Okay, we say that D is a complete metric. More precisely, if you want to say that on Vx, it is not only a metric; it's a complete metric. That means every Cauchy sequence with respect to the metric D converges in Vx. That was the thing, big thing to prove. Okay, and I told you that I will be using the actually continuity of the mod function. Now, so let Fn be a Cauchy sequence. Here you should understand that it is an arbitrary metric space. I do not know whether it is contained in a bigger complete matrix or not. So you'll have to show whatever information you have. Where Q was not complete, you knew that because Q was contained in R. But here I do not have any such facility, information. Be a Cauchy sequence in BXT. Okay. Now pick up any X belongs to X, arbitrary X, and then keep it fixed. Now look, Fnx minus Fmx by definition D Fn Fm. But D, this is a Cauchy sequence. So this goes to 0 as Nm tends to infinity. But this is less than this. That means, but this is in the real line. So that means Fnx, this, for given x, Fnx is a Cauchy sequence in R. Now look, in R means I am using this distance, mod, but this is complete. Since this is complete, there exists y, depending on x, of course. There exists this sign unique y, because every convergent sequence has a unique limit. So there, this means there exists. And when you add this, that means there exists unique. So unique y, but depending on x, such that Fnx goes to y. Okay, this much I've got. This y that I already told you, this depends on x. This y I'm calling fx. Say, call. That means fx equal to limit of this sequence. This is well defined that I did. So this way for each x I'm getting a fx. So I have defined a function this way. Look, I have used Cauchy sequence, how I have used the real line with usual distance is complete. So this way I have defined a function. So this way you don't need, only thing you need to remember that fx is this. Now I need to show first you need to show that f is bounded. Only then you go to fn goes to f in bxd. F is bounded. Because f is not bounded, then there is no point in trying with f. So first you show that f is bounded. Look, how will I do it? Okay, fine. You can choose when epsilon equal to 1. Given epsilon equal to 1, look, there exists n naught belongs to n such that t fn fm less than 1. This one has nothing to do. You could choose any epsilon for all nm greater than equal to n naught. So particularly you have t fn naught less than 1. Okay? But d fn naught, now for each x, look, it means what? Fnx minus fn naught x, this for any x, take any x belongs to x. Because this is by definition less than equal to this. Now this, okay, fnx, you remember that. I am writing that this follows from the triangle inequality. Okay, this is less than equal to, actually its mod is equal to less than equal to that. I am taking only without mod. So obviously it will be this fnx minus fn naught x. Okay, less than 1. So that means you are getting what? Fnx minus fn naught x mod, of course, less than 1. That is, we're getting fnx less than 1 plus fn naught x. Now remember that fn naught came from here. The fn naught is bounded. So particularly it means there exists m naught such greater than 0 such that fn naught x mod less than equal to m naught. So this was what I did. That is true for all x. So this is 1 plus m naught. Call it m. This is true for all x. So that means Fn is bounded. Sorry, what I needed to show. But Fn is bounded, that won't work. Okay, fine. But I needed to show f is bounded. Okay. Okay. But my calculation, look, this much I do not need. But I am showing that how you do this now. Now, look, what will you do? I have written a little bit differently here. Now, this you got, but this was true for all n greater than equal to n naught. Okay.
Yes, sir.
So that I can do this. Limit fn x n tends to infinity. That means for Lord is sufficiently large n, so that obviously that I can choose bigger than n naught, right? That will be less than equal to. In the limit process, it can be equal. Even though it's strictly less than, it can be equal. That I have given an example. For okay.
Yes, sir.
Got it. Okay. This I'm getting. Now look, I pushed this inside. This you are using what the result I have given you. I'm using the continuity of the mod function.
Yes, sir.
Got it? But this is actually, by definition, the way I got constructed. This is fx.
Yes, sir. Fx.
So this is true for all x belongs to x. So that f is bounded. Got it? Okay. So look at the trick. I have one is just for convenience. You could take any epsilon. It doesn't matter. But I have fixed one n naught so that I can argue. You could take anything, any fixed n greater than equal to n naught. I have chosen n naught. Okay. So right. And then you look here. This is the important thing. I'm using the continuity of the mod function. I post limit inside. This you'll have to be careful that whether you can do it or not. You need the justification. Okay. So that means f I have defined, that is bounded. Okay. So that f is really belongs here. Okay. Now I want to show that. Now to show fn goes to f. Actually, sometimes we write the metric d. That means with respect to this metric. Fn goes to f with respect to this metric. That is, I'll have to show that d fn f goes to 0 as n tends to infinity. Got it? That I'll have to show. Now look again the trick. Okay, what I'll be doing here. Okay. Bounded function हो गया, ठीक है? Now look. That means what I'll have to first is figure out what I'll have to do that. That means I'll have to show given epsilon, any epsilon, no, given epsilon greater than 0, there exists n epsilon, a natural number, such that d fn f less than epsilon for all n greater than equal to n epsilon. Okay. Actually, let me tell you, if you can prove less than equal to epsilon, doesn't make a difference. You could start with epsilon by 2. But still, I will show you that how, if you are very careful about, no, I want strictly less than epsilon, then you start from epsilon by 2. Okay. Now, look. So start with this epsilon. That means you'll have to start with epsilon. You'll have to find this n epsilon such that you have this. So start with n epsilon, but it's a causal sequence. So given this epsilon, there exists n epsilon belongs to n such that d fn fm less than epsilon by 2. I've taken. Okay. for all nm greater than equal to n epsilon. Got it? Okay. This is I'm using the fact
Yes,
that we have started with the Cauchy
Yes.
sequence. I'm just look with epsilon. I'm taking epsilon by 2. That I will always like I can do, because then later on I will get less than equal to epsilon by 2. So that will be strictly less than epsilon. Good thing. So, but this means what? Now look here. I'm writing what is the meaning of this. This means for any x, fnx minus fmx, this. ठीक है? Okay. Now this is for large nm greater than equal to n epsilon, means for large nm. Okay. Now you do this. So that limit m tends to infinity fnx minus fmx. In the limit process, it may be less than equal to. I have given limit 1 by n. Look, 1 by n strictly greater than 0. But when you take limit 1 by n tends to infinity, then that is 0. Okay, so it can be strictly less than this. Okay. This. But when you are taking the limit, then it comes 0. Okay. So this will be less than equal to epsilon by 2. But I am taking already m tends to infinity. That means I am taking large m. So all I need to write for all n greater than equal to n epsilon. M greater than n epsilon equal to again n epsilon, it is recorded here. Okay. So now that means you are getting this. Now look, that means what you are getting? That means you got, let me write it, limit fnx. You should be careful for which limit you are taking. Fmx m tends to infinity less than equal to epsilon by 2 for all n greater than equal to n epsilon. Okay? Like before, now this limit I can put inside. Now look, for the timing n you keep it fixed, because m tends to infinity. I am doing the limit over m, so it doesn't affect n. So that like limit a plus xn, if you take, that will be same as a is a fixed number, a plus limit xn, right? So that first you put the limit inside. Okay. So that means it will actually, I will get fnx minus limit fmx m tends to infinity. For the timing, you are taking any n greater than equal to n epsilon, but you are not touching n after that. It will be less than equal to epsilon by 2 for all n greater than equal to n epsilon. Here I should write for all x belongs to x, because this was valid for all x. Okay, this is very vital. Okay, and for all x belongs to x. But this is by definition of the function f. I defined fx, right? M tends to infinity, n tends to infinity, doesn't matter. The only thing this you'll have to check. This is m here, this is m here. So that I am getting fnx minus fx less than equal to epsilon by 2 for all n greater than equal to n epsilon, and for all x belongs to x. Fine, but that means what? Soup of, because for all x, that's why I'm saying you should be careful from here. Should write for all x belongs to this. Soup of fnx minus fx, x belongs to x, that is less than equal to epsilon. I have taken already soup, so I don't need that. Only thing I need to write this. Got it? But this is what? By definition, d fn F. Right? That I have got. dfn f less than equal to, sorry, epsilon by 2. That means I have got this. That is, you will get this. I took epsilon by 2, but in the note is less than equal to epsilon. In the definition of the convergence of sequence, less than epsilon, less than equal to epsilon, same thing. For all n greater than equal to n epsilon. That is precisely so Fn converges to F. Got it? Look, here also I have used that I am pushing the limit inside. Okay. So I have used the continuity of the mod function so that you have got a good result, big result, that Pxt is a complete metric space. For complex, I told you complex value is exactly the proof will ditto work. Complete metric space. In fact, in the proof, there is no, you won't need any change if you replace R by C. Okay, right? Okay, now here is a special case. In function analysis, measure theory you will need. Suppose x equal to n, set of naturals. That means you have the function. Here I have taken real valued function. But any function on n actually is a sequence, right? And I have taken bounded function. That means bounded sequence. That means Bn will be what? The linear space, vector space. Like function you are defining adding pointwise. So here the sequence actually will be adding coordinate wise. The linear space of bounded sequences. Of all bounded, sorry. Bounded real sequences. Okay. Right? Bn is the linear space of all bounded real sequences. Okay. And the metric will be what? Look, here that means if you take a sequence x, xn, y, yn. Now the function of the sequence, so I am taking this thing. So here t is coming what? Xn, yn, this soup of, here the coordinates of the sequence, they are actually the value of the function xn, basically this fn, right? Yn is gn. So that this is soup of, okay, this is coming xn minus yn, x is n, so over all n. It means over all n, or you can write if you want. That is the thing. Okay, this is the d here, soup of this. Got it? For the special case. Okay, so this is complete. And here we did not use the notation bn. In mathematics, there is a special notation L infinity, because this metric also called infinity metric, L infinity. Okay, look here I am doing over real, so sometimes people write L infinity R in order to indicate that we are taking real sequences. On the other hand, if you take complex sequences, you write this. But if you do not bother whether real sequence or complex sequence, anything will be valid, then you simply write L infinity. Okay, got the point? L infinity R, L infinity, it means all real sequences and it means all complex sequences. Usually in notation use this. Here I should tell you that this is a standard notation, but some people put infinity superscript on the top, but they are the same thing. Here the same thing. It's a matter of choice, taste, that whether you will write infinity as a subscript or superscript. So this is L infinity. So L infinity, that I told you, L infinity is a complete metric space. But I am giving you this example. I have already defined separable metric space. Check that. L infinity, whether it is over or not, okay, that means D, this metric is not separable. Think about it. If you can't do it, you can ask me on Friday. Make sure the Friday don't miss, because that will be my last class before your exam. And I'll talk about the syllabus. I'll talk about which topic you should put your emphasis on. Samajh gaya? Okay. L infinity, this is not separable. This is a very vital fact. Sometimes you need negative facts. Negative facts, they are often helpful in mathematics. So don't think it's a bad space. It is not a bad space. It gives a lot of examples in that. L infinity is not separable. That means if you take, in fact, it can be proved. Whatever countable subset you take, it won't be dense in that. Okay. Well, I can give you some hints on that. Suppose you are taking a countable set, N infinity. Look, the way, if you remember the proof, this is not countable. Okay, that look. Suppose A, you have n elements, sequence. So you are taking this one, first sequence, x1. That means this is this. So in general, coming, if you have xn, sorry, actually some people be careful, they put a bracket so that it is not a power. Understand? So put a bracket, indicate, so that it should be a bracket. You can take. Okay, the component. So xn, you're taking, it will be now look, play with the game. Now you construct a new sequence. Construct a sequence. Define yn in terms of this. You can think of that. I don't know. I'm just giving in this, whether this will work. Okay. But you'll have to check you are getting a bounded sequence. Okay. So that you'll have to check. So, and see that this doesn't belong anywhere, because this is different on the nth position. Okay. Yes, so sir. It is different. But if you take that left side and ball, each ball should contain a member of this. So in the ball, if you take the radius less than 1, that is the trick I'm doing. Less than 1, that don't contain any of these members. Look, it is a supremum metric. Okay, so think about it. Okay, so that again here I am playing the diagonal argument. Okay, I am doing this. Okay, yes, so what are you saying?
Yes, sir, there is a diagonal argument. Yes, sir, there is a diagonal argument.
We need to work on that. You check it. Okay, right. Yes, this I have given one example. You can put it, define it different ways than that. But the point is that it is a diagonal argument. Okay, that's why I mentioned it. Okay, here also I wrote that this space L infinity is very important in measure theory and function analysis. Fine. Okay, so that my OL, let me tell you in that these BXD and L infinity, make sure that you read it very carefully on the technique and that. I will give a question on this. What I am telling you, I will keep my promise. Don't think it is the leaking of the question paper. You should be able to figure out that what I'm saying. It's not difficult, it won't be difficult, but you'll have to understand. No mugging up will help. You'll have the note in the exam. You'll have access to the book. You'll have access to the net. But let me tell you that whatever help you take, you should acknowledge, you should write. Even from the net, we have taken some source on that. Okay, you should acknowledge. But if you do not acknowledge, and if I find you have taken help from them, then I will deduct the marks. Okay, so this is very important that you acknowledge the source. Okay, then I will appreciate it. Okay, so that here, this is my favorite, because it is measure theory and functional analysis, both are important. Both areas are important. So I will give a problem on this. Okay, so you read it very carefully. I have explained the whole proof. You can't blame me that I didn't explain that. Okay, now in R, we defined cluster points, okay, of a sequence. And actually you showed that cluster point is actually subsequential limit. Okay. Well, subsequential limit for a bounded sequence, you got the lowest cluster point and largest cluster point. Of course, in a metric space, we do not have that partial order in that, so that I can talk about lowest and largest. But look, how I defined cluster point there. Okay, same way I can define cluster point, because in order to define cluster point, I just needed this thing, and this you replace by D, and precisely you will get the cluster point of a sequence. So if you take this will be, then X is called a cluster point of X. If given N, here two things you have, given N and epsilon greater than 0, there exists K greater than N, such that K depends on both this K. Actually, here I am saying K greater than N, of course it will depend on epsilon also, such that D xk x less than epsilon. Okay, look here, I took in the real line this. So in the definition, you are just replacing this by D. That will get a cluster point. And like every cluster point is a subsequential limit, and subsequent limit is a cluster point, that's the theorem. Let X be a sequence in a metric space Xd and X belongs to X. Then X is a cluster point of Xn if and only if there exists a subsequence Xkn of X such that Xkn converges to X. Okay. I already said copy the proof of theorem 4.4 of pages 23-24 in AB, Aliprantis Parkinson. But don't forget to replace this by D. Okay. And page 7898 पहले दिया मैंने न क्या कौन सा पेज में है एक मिनट I didn't mention the page. Let me see that. Which page is this? Do problem 7, 8 in the list of the problems. Wait a minute. Did I? There is a problem list in the 7, 8, 9, 8. I should check that. I forgot to mention the page. I think this is, wait a minute. Page. कौन सा पेज में पढ़ा रहा था? I think, let me tell you that.
Page 7.
Huh? Do you have any idea?
Page 7.
Page 7? But I am doing a geometric space on that. How it can be? I am talking from the book and that. Oh, I think page 47 of the book. Write it there. Page 47. 7 is the Cauchy sequence. 8 that I mentioned in that. Okay. And prove that closed interval is uncountable by using the Cantor's theorem. Okay. Yes, 7, 8, 9, 8. This is page 47 of AB. Okay. In the book, page 47. Okay. Here I should mention that it is saying that first problem, that suppose in a metric space you have this, and suppose you have two sequences here. Okay, right? And suppose xn, yn are Cauchy, they are Cauchy. Problem is asking dxn, yn. Look, this is a real number. Okay, but for each n, so this is a sequence in the real line. समझ गया? So this is a sequence in the real line. The problem asks show that this is Cauchy. That means Cauchy in R. That means you'll have to show that dxn yn minus dxm ym. These are the numbers, real numbers. This goes to 0 as nm tends to infinity. Got it? That you'll have to show. But the nice thing is that you'll have to use this Cauchy sequence. But before that, you'll have to use the triangle inequality. Look, how will you use triangle inequality? xn, yn Cauchy. xn is Cauchy, so you will plug xm here. That means you will have something like this: dxn, xm, xn yn तो ठीक है, पहले dxn yn है, plus, but you have taken this, I think you will have this thing, minus dx xn xm, then you'll have to go for this thing. Okay, so you'll have to give this something and minus on that with this triangle, because here you will be able to use Cauchy sequence. Similarly, you'll have yn. Okay, you'll be able to use Cauchy sequence. So that you'll have to do it. But the one thing you should note that though they are Cauchy, they need not converge here, but ultimately this will converge because R is complete. Understand? Okay, so that this question I can also ask, if they are Cauchy in that, show that this converges in R. समझ गया? Okay. Make sure that page 47. Forgot. Write it. Now, next page you see that 96. I'm talking about the distance on that. So this is very important. Okay. So you're starting with a metric space Xg, and in YAL, suppose you can take non-empty sets, non-empty. Subsets of X. How will you define the distance between two sets? Look, here I have distance between points, but here I'm trying to define distance of between two sets. Okay, first of all, look at this simpler case, distance between X and the set A. Okay, I have given a diagram on that, high school geometry on that. What should be the natural definition? Okay. First of all, forget about this figure. Suppose you are in front of a classroom. I think you have faced that situation, though now during this corona you are having online class, but you had offline class also in your college. Okay, so that suppose you have not entered the class, but you are in front of the class, then classroom, then how will you calculate the distance between classroom and you? You are standing outside classroom. Okay, look, classroom is like something this space. It's a subset of R cube actually, right?
Yes, sir.
Yes, sir.
But when you suppose this is your room and you are here, how do you calculate the distance? You look, obviously you won't say this distance, you only say this distance, right? This one.
Yes, sir. The closest point.
That means if you are drawing all the points from the distance here, that means you will choose the smallest one, right?
Smallest. Yes, sir.
Yes.
So that exactly the thing we define here first. That means here it may be the infinite collection. So I'll take infimum. Infimum of dxa, where a belongs to a. That's exactly the natural definition. Or you can write simply this way. dxa, a belongs to a. That exactly do. So that means you calculate all the distance between x and the points of big A, and then you take the infimum. Okay, that's the distance should be. In fact, what I'm telling you in high school you did, like you have a line, that's the example I have given. You have taken this and you said, okay, I take this. What is the distance between that? You have taken the orthogonal projection and you said this is the distance. Okay, if you have this is the point. But what does it mean? Look, on the line, here the line L is your set A. Okay, you are doing an R square and you are adding all these points. Look, this will be the smallest distance. समझ गया? This orthogonal projection. So that is the same thing we are doing. Okay, I do not have any concept of right now projections, anything in the metric space on that. But look, ultimately we are taking the minimum distance. So here also it is consistent with that. That is distance between dxl, between the point x and l, you are taking this. Infimum of dx y belongs to l. Okay. So that is the distance. Yes. Okay, so don't forget, this is the first distance of a point from a set A. That means this is definition. This is definition. Okay. Now, look, the first thing you can do it, suppose Xt is a metric space, you can prove just by using the definition. Or you can use the definition of closure point. Suppose X belongs to X and A is a non-empty subset of X. Then X belongs to a bar. Okay, if and only if dx is 0. That is very natural. If you are standing just next to the door of your classroom, what will be the distance? You will say distance is 0, though we are not in the room. समझ गया? Okay. Yes. So this don't forget, this we use very often in function analysis. We'll be using. Okay, X belongs to a bar if and only. Just use the definition, you will get it. Okay, I'm not going to prove it. I think I have given it an exercise on that. Exercise on B. Okay, DAB I will come later on, but that I'm doing. But here I have given many exercises. Make sure, let me tell you that. I will give problems in the exam from the distance. Okay, at least one problem will be there. It may be more. Okay, so make sure do all these problems. Okay, before that, let me tell you that. So this you get what this is giving you the closer point, right? Okay, think about it. I don't know. I don't have that last. If you have the senior, you can ask them last year's questions. I have given them in the minor, I think. But what about interior point characterization? Interior point. And boundary point. Look, remember that. If you have a interior of A is what? It is what is interior of A? X minus
A closure.
X minus A, its bar. Got it? This is your X. Suppose this is A. So X minus A is here. From that, the boundary is coming. Basically, you'll have to give them deduct the boundary points. So interior of A is this. Got it? So that, but here it's a closer point, but for this, A replaced by A minus A. So this way you can characterize interior point of A in terms of the distance. Got it? Is it all right? Now boundary of A, you'll have to see that this is this. Got it?
Yes, sir.
Or boundary of A, you can think of this also. This will be what? A bar minus interior of A. Okay. So if one of them, if you can, that means here it's not two problems, one problem. If you can do this interior of A, then by this you can do, because you know A bar. Samajh gaya? Okay. So
Yes.
think about it. That how to characterize interior point, boundary point in terms of distance function. Got it? Okay. Make sure you do it. Okay. Now look here, when the distance, usually people do it this DAB. Again, look here you have two sets. And if I say distance between that, what I'll do? I will always basically come, this will consider as distance, right? It's not something here and here, right? Okay. That means the smallest distance. That exactly the definition I've given. That you calculate, suppose this is A here, it is B here. You take all the distances, you take the infimum. Infimum of DAB, where A belongs to A. These are natural definitions. You won't have to think about what should be the definition. You just think about R square, R cube. That will give you the idea that why its definition should be this. But look here, I am giving the distance between two sets. But I could also have this distance calculate this way. First you keep it this, suppose this is we call B. You keep it fixed. And then from each point of A, I calculate this. Okay, that I have already defined, right? Okay, all calculate. And then I take the infimum of this. This A belongs to A. This is set A. That is another distance function I'm getting. First we are calculating DAB, it makes sense. Okay, right? Look, infimum is, this distance is always defined because it will be greater than or equal to 0. It is not supremum. So whether A is bounded or not, it will be always defined. Got the point? It is never undefined. Okay, for empty set we can try to define, but for empty set you don't need to bother. You don't need to define. Right? Okay, for non-empty set this is always defined. So you can have this. Similarly, if I interchange the roles of A and B, I have this thing. I have another distance. DBA. क्या हो गया? B belongs to P. Look, this is the question I have given in A that show that these are all equal to this. समझ गया? So that if you go at one stroke, if you define this, or if you go step by step, 2 steps, this will be the same thing. Okay, right? So that this is fine. This should be able to prove it. Part C, that is follows from the definition, diameter of B and that. If A less than contained in B, then relation between distance of B and dxB from a point. Suppose you have this A, B, two sets, another point takes here. Then how these will be related? That's a relation 6, C I have given it. But now look T. T is very simple to prove, but be careful. That I said that look T, X, A, D. You should be able to prove it. T, X, Y, D, Y, A. For all Y belongs to X. Okay. Right. Be careful that how. Look here, you will be using the infimum. So that's why infimum supremum. मैंने एक तो bx बोल दिया. Question I will give. Or maybe the L infinity. और एक question बोला तो minimum here distance. Function. Related to that infimum supremum. So I will give specially a question on infimum supremum on the real line. 3 question बोल दिया. Okay.
So total number of
questions will not only that 3 questions, that will be at least 25 marks. Okay. What are you saying? Say again.
Number of questions.
Number of questions से क्या पता चलता है? 5-6 questions will be clear. I am very careful about the time also. It's not that you won't be able to finish it. Okay. Look, usually what I follow, 1/3 question will be simple question, very simple. 1/3 and another 1/3 will be, you'll have to think little bit. It's not that you'll have to think great. Another 1/3, you really need to know the subject well. So 2/3 should be in your immediate grip. 2/3. समझ गया? Okay. And about the time, that's why I increase the time. Because that time I used to give for 25 marks question. Then I later on realized it is 40 marks paper. So that's why I increased 1 or 30 minutes. Okay. And you are having 15 minutes. I do not think you will need more than 5 minutes to send me. Okay. So basically 1 or 40 minutes you can write. Okay. So 100 minutes. So I think you will have enough time. 1 or 2 questions, I am telling you that for the students who really enjoyed this course, who understood this course, everything, conceptually understood everything, not only mugging up and that. But they are not difficult problems. I do not give difficult problems. But I gave, you'll have to think. You'll have to think. So, समझ गया? You will realize, you can ask your seniors that what kind of question. Okay. Look, I will give a question. When I choose a question, my first expectation, even if it is so-called difficult, tricky, I will expect at least one student in the class should be able to solve it. If I know that nobody will be able to solve it, I won't give that question. Okay, so that's why before giving any question, I myself work out. And even if it's not a difficult question, but working out, it is coming messy or little bit complicated, I won't give that question. Okay, because in the exam limited time, it is difficult to work out everything. Okay, so I won't give that question. So that here, coming back to this, make sure that here infimum is important. So you should handle infimum and triangle inequality carefully. Okay, on the infimum, simply don't put triangle inequality. समझ गया? Okay, so here how to do that? Okay, let me see that. Let me give an idea that how to prove it. So look here, A is any point on that. So here you keep any A, pick up any A and keep it fixed, arbitrary. Then you look what I can get. T x A by triangle equality. T x y T y A. Got it? This will get triangle inequality. But look, if I take infimum over this, then here it will come, it will go. How will I know this will be same thing? Infimum, the try still inequality will hold. That you should be careful that how to handle it. Okay? How to do that? Here I am getting this. Okay. How to do that? How to handle it? This say, if you keep changing, I said you can pick up any A, but then if I take this, how to do that?
Over A.
Over A, but infimum it will come this. But here also infimum will come this. How to handle this in two places? Infimum is now greatest lower bound. First you'll have to show it is a lower bound. Okay, right?
Yes.
So how to do that? So will it work on that? So that you'll have to think that. With triangle inequality, don't mix up with infimum. The infimum will that you'll have to be careful how to argue specifically. Understand? That's exactly the problem here. It's a small problem, but you'll have to be careful how to handle it. Okay, right? That you'll have to be careful. That how
inside
to
infimum ले सकते हैं.
हाँ?
Inside infimum ले सकते हैं. D of x, comma infimum of A.
Okay, if I take this, this is so actually dxa will be this by definition, right? So this is this. This makes sense. You are keeping up in any A arbitrary and then keeping it fixed. But this is true always. So that means I am getting dxa less than equal to dxy plus dy. ठीक है? Got it?
Yes.
Now look, now I will vary A, but still how will I do it? dxa minus dxy less than equal to dya. ठीक है? This is true for all A belongs to A. That means this is a lower bound of this. समझ गया? Okay? This is a lower bound of all these things. And infimum is the greatest lower bound. So that it will mean dxa minus dxy will be less than equal to dya. Got it? That is the proof. That's why you are getting here. समझ गया? Okay. So in particularly you are getting what? dxa. So be careful that how I did the trick. Okay. Here I have used the definition of the lower bound. Here I have used the definition of the greatest lower bound. This is a lower bound and I am taking the greatest lower bound. So this is this. ठीक है? Sorry. Got it? But I can interchange the role of x and y. I didn't have, I just had names x and y. Okay. They are not very specific. So that means its negation will be also less than equal to this. That means what I'm saying, if I interchange the role of x and y, okay, I will get tya minus dxa less than equal to here dxy dyx, but dyx is same as dxy. Okay. When you say absolute value less than equal to this means what? This value and its negation also both are less than this, right? So this is negation of this. That means what I am getting. That means I am getting this. Got it? This is an important result. Later on, we will define continuity on metric spaces. We will see that this says distance function, metric function is continuous. Okay. Look, dxa, look, it is given a function. Look, you have a metric space xt, and A is a subset of X, A you assume non-empty. Then what I am getting a function. Look, I am getting this function X to R. X, usually we write FA, indicate that A is involved. Dx, right? I am getting a function from the metric space X to that. So here R is no problem, but here is the metric, so I'll have to define that. After the exam, I'll do that. That definition of continuity of a function between two metric spaces. Here I have a function between FA, between two metric spaces, dxa. But look, dxa, in some sense, continuity, what you talk about, what actually continuity gives. Look, that means if xy becomes close, if they're close to each other, that these values, fa also close to each other. Got the point? This says that if xy, distance between x and y, if they're close to each other in x, then their values of the functions are close to each other. Actually, continuity intuitively means that points close in the domain should go to the points in the range close to each other, not very far off. If it's very far off, then so-called we call discontinuous. Understand? Big deformation. That means deformation you can have, but that has to be continuous. That means small deformation, you should have a small deformation in the range. It cannot be a big change. That means continuity. Look, even when you do for a function and that, if you say continuous means what? Basically, intuitively, you need, if you have a small change here in the value in xy, small change, then in the value here fx, fy, that there should be a small change. That means this. If you have a small change here, x minus y, here you should also small change. That is the idea of the continuity. The change cannot be very abrupt. Change cannot be abrupt. That is the opposite, antagonistic to this continuity. Continuity intuitively means that small change should go to small change. Understand? So that way later on we'll see that the distance function is continuous. Okay. So that all these things you should do it. And if you see that what I've given, if distance between DAB is less than equal to dxa for any point plus dxb. This all you'll have to use the definition of the distance, nothing else. But be careful that infimum, how do you use it? Don't directly post triangle inequality on infimum. You'll have to justify infimum when you're going to use infimum with triangle inequality. First you'll have to do with a lower bound. You have to show lower bound, and then you'll have to show that infimum is the actually greatest lower bound. That means GLB. Here this term, if you remember this, it will be better. GLB. That you'll have to think GLB. Only that way you can push that. Okay. I have already discussed on that. Anyway, just two problems. Let me discuss them. Look, G and G. I said distance between the union I have given. Okay, that means I said dx union AI. This is an arbitrary collection of sets. Finite, infinite. Then is infimum of all these things. Okay. This you can prove, just you'll have to use the definition of infimum. But the point is that I said for intersection, what happens? I said for intersection, it is not true. Actually, you can do high school geometry. You see, in R square, you have it. Okay? You have this. You take two circles, unit circle here. You touch here. Okay? So that its intersection will be this point. Got it? Okay. My diagram is pretty bad. So unit circle. You can take unit disc also, whatever you want. That means with radius here, actually it is, the point is what? This is 1, 0, right? And this is minus 1, 0. And radius is 1. ठीक है? Okay. Now, ये थोड़ा सा ये हुआ. Still I am doing nonsense. थोड़ा सा is like this. I want to do it. Okay. Here you should have the same thing. But here you take the point 0, 1. ठीक है? समझ गया? See ये circle C1 लिखो, C2 लिखो. Okay. At this point. So look at what will be the distance. ये तो it should not be difficult. You should take a tangent somewhere. Distance between what I'm saying D01 and C1 and D01 C2. I think in high school geometry you can able, what will be the distance here? Basically you need a tangent here, that distance. Okay. Similarly here. ठीक है ना? Okay.
Yes.
And what will be the look? This intersection is this point origin. That distance is 1. Okay? But I think, I'm not very sure, calculate it. It will be root 2 minus 1, I think. I'm not very sure. This should be also root 2 minus 1. So infimum of this distance or supremum, if you change by supremum, okay, this is not true. So that it will be true root 2 minus 1. I think so. I'm not very sure on that. Last night I was just thinking about it in my mind, head of the calculation. That you should check.
So 1, 0 and 0, 1 को add करके.
नहीं ये नंबर ठीक है ना, ठीक नहीं है?
Yes sir, root 2 minus 1.
अच्छा ठीक है, that's good. That's good. But this distance is coming 1, the intersection. Got it?
Yes sir.
0, 1 to 1. So it is not coming any of them, whether you take sup or inf. Okay. In fact, you would like to change this thing. When you take this intersection, basically you will be taking this. समझ गया? But this is not true. For infimum is also not true because both are coming same. Okay. So that I have done that. Basically intersection, the result is not true. Okay. But question 2, you know that what I have given. Question 2 is easy, but you should do it. Suppose S is a non-empty subset of R. If S is bounded below, So S is bounded below mean infimum S exists. Okay, I said D, so that infimum of S is bounded below is 0. I asked you to prove that. Okay, I think this you can do it. Make sure जो सब distance दे दिया ना, सब करना है, ठीक है? And Friday,
Yes, sir.
I will just introduce a little bit the concept of continuity. I won't teach you any theorem, but I am saying Friday is just before coming, read my pages, page 101 and 100 and 101. I think page 99 is missing of that. My case is that. Let me see that what I wrote then. Continued on page 98. Oh, 99, 99 and 100 एक axiom of choice note पहले ही तुमको दे दिया मैंने. Axiom of choice. AC.
Yes, sir.
99 and 100. That's why I was wondering. Okay, so पहले दे दिया. So 101 में तुम first 2 pages you read it. Because I'm telling you, it is not only for my course. You should have the clear concept, ideas of the continuity on that. That I have tried to explain that continuity. Continuity, first of all, in mathematics, let me take 2 minutes in that. Any space wherever you're considering. Now the thing is that I should have a vehicle to move to another metric space. So Y row. How will I move from this and that? Even linear space, when you have the linear map, what is the idea of that? Basically, it's a vehicle, car. You are moving from one linear space to another space, linear space. That is also in algebra, you do that. For the group, ring, group homomorphism, ring homomorphism. Basically, you move from one group to another group, move from one ring to another ring. But the point is that you may ask, why do I need to move? First thing is that, why we need to move? Because if we want to study a group, it may be that the group we have been given or linear space or metric space, that may be difficult, at least at the first glance, to study, to look at it. But if I move to another, that may be the easier. Okay, then I will study there, and then I will try to come back again on to the space which I started. And I see the what information I got the second one, whether I can have my original one. That's the way the definite map. It depends on the structures. Look, you are doing algebra, linear algebra, but basic idea of group homomorphism or linear homomorphism, the same thing. Okay, linear homomorphism reflect on the linear structure, whereas group homomorphism reflects on the group structure. Similarly, here you will have a map. How will I move from a metric space to another metric space? That should reflect on the structure of, here the structure is the metric structure. That should reflect the metric structure. So a quality of the map, a character of the map will be determined by the structure of the spaces you are considering. Okay, but here since the metric is that, here natural move will be continuity. Okay, so I will take class on Friday. That will be my last class before the exam. But make sure if you have any question, of course you should meet the TA and you should ask them for extra TA. Whatever I have in my notes, questions I left, query I left, that you should ask them. But you can ask me. I will answer your queries and questions first Friday. Okay. Then if the time is left, I will talk about little bit about idea of continuity. The 2 pages. So make sure you come prepared with your queries on Friday. Whatever I taught until now. Okay? Okay. Bye.
Okay, sir. Thank you, sir.
Okay, sir.
बहुत पढ़ा.
Okay, sir. Thank you.
पीछे तुम गाली दोगे. ये टीचर बहुत पढ़ाया.
नहीं सर आपको बहुत पढ़ाया.
वो मुझे मालूम है.
Sir, I have one doubt.
Actually, let me tell you one thing from my experience. Student जब कोर्स लेता है वो टीचर को बहुत गाली देता है. जब कोर्स पास करके जाता है कोई नौकरी में जाते वो सोचता है अरे ये टीचर ने पढ़ाया ये मुझे लगता है. So in the short term जो टीचर पढ़ाता है वो गाली खाता है. But in the long term the student appreciate that. That okay, I have taught this. ठीक है? Okay, so तुम गाली मुझे दोगे तो वो ठीक है, I accept it. Whatever I do, I try to teach you. I try to teach you something so that you learn something. समझ गया?
Yes.
Okay. Whatever
Yes, sir.
you do it. So sometimes you may even go for the banking job. Here there are some M.sc students, they go for banking job. But you will appreciate later on, okay, this I have learned and that. I have a student, an undergraduate student, our BTech M.tech. He works in London in financial company. वो पास आउट किया 2003 में. एक बार 2010 में, I think around 2010, he came to my office and see Prasun Joshi. Hey, do you know what he said? He said, whatever I learned here in the IIT, I forgot. Only thing I didn't forget your courses. Because you need to give so much trouble. He wanted to make sure that we learn something. That's a certain things I remember about your course. But other courses I do not remember. Okay, that's a compliment. You understand? So
Yes,
whatever
sir,
I teach, at least not everything, but at least part of the things you'll remember throughout your life. Okay? अभी तुम मुझे गाली दो, ठीक है? Okay, bye.
Thank you, sir.
Thank you, sir.
To your
Thank you.